Hello class, this is an example of how we can apply the central limit theorem. Let's go ahead and read this problem. It says an instructor knows from past experience the time it takes to grade one student paper is positively skewed, which is non-normal, and then has an average of 6 minutes and a standard deviation of 7 minutes. Okay, so let's go ahead and break down this sentence. Essentially, this is talking about a population. It says from past experience, it knows that this random variable, which is the time it takes to grade one student paper, has a positively skewed distribution with a mean of 6 and a standard deviation of 7. So this is the population information. So definitely not normal. So let's keep reading. This term, she has a class of 49 students. She decides to budget an average of 8 minutes per student paper for grading. What is the likelihood she has not budgeted enough time? Well, given this is now talking about a smaller sample size, so this is talking about n equal to 49, that's 49 students, and it's talking about a sample average, so the average of 8 minutes per student per paper for grading, we're going to then know that this is now going to be a central limit theorem type problem. The reason being is that now instead of talking about the entire population, we're talking about a sample size and a sample mean. So we have a sample of 49 students and a sample mean of 8 minutes to grade an individual paper. Now, something we know from the central limit theorem is that if n is sufficiently large, so if n is essentially greater than 30, then the distribution of x bar, so x bar will be normally distributed. This is the distribution of x bar here, will be normally distributed with a mean of the true mean. So in this case, mean is equal to 6, and a standard deviation of sigma of x bar, which is equal to sigma over the square root of n. So in this case, again, sigma is equal to 7. That's the population standard deviation. Now we have to count for our sample size. In this case, that's 49. And this then is equal to 7 over 7, which ends up being just 1. So the standard deviation of our sampling distribution for x bar is equal to 1. So if we want to do one standard deviation up from the mean, that's going to be 7. 2 standard deviations up from the mean will be 8. 3 standard deviations up from the mean will be 9. And do the standard deviations down to, I like to write all of my normal distributions like this, and then that way I can easily visualize the proportion that I am trying to find. All right, so let's go ahead and reread what the question is asking. It says, what is the likelihood she has not budgeted enough time? So what does that actually mean? Well, that means that the probability, we want to find the probability that our sample average, so 8, what is the probability that it'll actually be greater than 8 minutes? That means that she didn't budget enough time. So let's go ahead and shade in that region. Here's 8, and we want to find this area under the curve. Well, there's a couple of ways that we can do that. We can eyeball it, but that's not really going to give us an exact answer. So what we should do is we should standardize this distribution. All normal distributions can be standardized to be a standard normal distribution. So let's go ahead and standardize this score. So what we want to do is we really want to find the probability that x bar is greater than 8 minutes. This is then equal to, if we standardize it to be a z-score, the probability that z is greater than x bar minus our mean, all divided by the standard deviation of x bar. So when we first learned normal distributions, this is just x minus mu over sigma. Well, now our random variable isn't just x, it's x bar. So now our z-score is x bar minus mu over sigma of x bar. So because we've already calculated this, we know that this is then going to be the probability that a standard normal distribution, z-score, is then greater than x bar, which we have is 8 minus our mean of 6, all divided by sigma of x bar, which is 1. This ends up being the probability that z is greater than 2. Okay, well, something that we know is that if I were to look this up on a table, I wouldn't quite find the right value. I know that my standard normal table will always give me the area that falls below a particular score. So let's go ahead and look up the area that is associated with 2 on our standard normal table. So if we switch over to the standard normal table and scroll until we find a z-score of 2, we can see that the z-score value of 2.00 is 0.97725. 0.97725. So this is then the area that falls below 2, 0.97725. However, we didn't want this area, right? We want this area. This is why the picture is so helpful. And so how can we find this? Well, we know that under the curve, the total area will be 1. And so if we want to find this area, we can simply subtract this value from 1. So 1 minus 0.97725 is going to give me a value of 0.02275. So that's this area over here, and that seems to make pretty good sense, because that looks like a pretty small proportion of the total area under the curve. And so what that means is that there's a 2.275% chance that she has not budgeted enough time. That's a pretty small chance, so I think by budgeting 8 minutes is okay. That seems like a pretty good estimate, maybe even a little bit high. She could even maybe go a little bit lower. All right, hopefully this example helped you understand how to apply the central limit theorem. Essentially, this central limit theorem is one of the most important theorems in statistics, as it allows us to assume a normal distribution for several different concepts, including confidence intervals and hypothesis testing.